Now I invite Arudra to give a brief introduction about our resource person for the second session.
Thank you, sir. Good evening, everyone. It is an absolute honor to introduce our esteemed chief guest, Ms. Aarti Sahayaronas, a distinguished expert in power systems and grid management. She currently serves as the Chief Manager at Southern Regional Load Dispatch Center, Grid India, playing a key role in ensuring the reliability of our nation's power grid. With 11 years of experience, she has excelled in power system protection analysis and power market operations. She holds an MTech in Power and Energy Systems from NIT Karnataka and has contributed significantly to research in areas like grid protection, renewable energy integration, and transmission system analysis. She has also led multiple protection audits across major substations in southern India. We are truly privileged to have her with us today. Let us give a warm welcome to Ms. Aarti Sahayaronas.
Thank you, madam. So I hope my screen is visible.
Yes, ma'am. Visible, ma'am.
Yeah. So dear all, very good evening. So welcome to the session on the overview of RE and its impact on protection issues in Southern Regional Grid of India. So this is the outline for the presentation. So I have one slide on grid management in India to just tell you about what our company is all about. And we have one slide on the All India RE penetration level, and then a couple of slides on Southern Regional RE details. Then we will be jumping into the protection related issues with respect to RE. So some of the things that we are going to cover in today's session will be on the impact of RE and earthfall protection, distance protection, auto reclose, protection coordination related issues, LVRT non-compliances, the reactive and active power responses during the fall, and finally some overvoltage issues in RE pockets will be discussed. So I hope the session will be interesting because all of these are based on the real cases, what we have observed in the grid during day-to-day operations. So to begin with, about the Grid Controller of India. So we are we take care of the grid management in India. We are responsible to ensure integrated operation at both regional and national level. So if you consider the grid management in India, we have the system operators at state load dispatch center level, regional dispatch center level, and national load dispatch center level. So there are 33 SLDCs, the state load dispatch centers, and 5 RLDCs. So I am from Southern Regional Load Dispatch Center, one of the RLDC. So if we talk about Grid India, all RLDCs and NLDC will come under Grid India, and we are like independent government company. It is called like ISO, Independent System Operator. And we are governed by the regulatory framework issued by CERC and the Indian Electricity Grid Code. And our financial autonomy is based on the Central Electricity Regulatory Commission's fees and charges regulations. So some of the functions of Grid India are mentioned here. So that is a quick intro about Grid Controller of India and SRLDC. So next, just I have put this slide to give you a quick number regarding the installed capacity in RE. So presently we have 146 gigawatt in all India installed capacity RE. So our maximum demand met all India level is 250 gigawatt, and RE penetration level, if you see, installed capacity is 146 gigawatt. So that is what we are seeing in the left hand side. The solar and wind installed capacities are shown here, and in India we have 12 number of REMCs, renewable energy monitoring centers. So in these 12 REMCs, 115 gigawatt of renewable is being monitored. Of that, 35 gigawatt is at inter-state level, for which the scheduling is done by Grid India. And you are seeing one image on the right side. So that shows about the so far how much we have achieved in RE, be it the instantaneous penetration, day-wise as well as annual energy met. For example, if you see the pointer, if you take the figures of Tamil Nadu, So we have met instantaneous RE penetration up to 77%. That is 77% of the demand met by Tamil Nadu at a particular time, because it's instantaneous. At a particular time, that megawatt was 77% from RE. And in terms of energy, 50%, meaning some 50% of the MU from RE divided by the total MU consumption of Tamil Nadu. So that was the level of penetration we have reached so far. And annual, if we see, 19% of the total Tamil Nadu consumption is from RE, we can say like that. So this is these are some numbers to have a feel over the RE penetration in India. So now let's go to the southern region. So when we come to southern region, out of that 146 gigawatt, 57.6 gigawatt is from southern region itself. So we are the region with highest RE installed capacity. And other peculiarities of southern region are like we have lift irrigation projects accounting to some 9 gigawatt, and we have pumped storage system. Presently 2000 megawatt is in operation, and this upcoming we have some 5.5 gigawatt, of which the Pinnapuram project is almost done. They are in the testing and commissioning stage. And some other peculiarities are like we have the first VSC based, voltage source converter based HVDC in India, which is nothing but the Raigarh-Thrissur link. And the maximum unit in southern region is Kudankulam, 1000 megawatt. Presently we have 2 units. So these are some of the peculiarities. Next, this is to show the demand variations in southern region. Usually our demand will start rising in Jan, and the peak will be in March, April, like that. So now we are already towards the peak. Already 65 gigawatt we have reached. Last year the maximum demand met was around 68 gigawatt. So this year we expect around 73, 74 gigawatt, and afterwards it will reduce. That is how it is. Just to have a feel on the system. So the total last year the maximum demand met was 68 gigawatt, and in terms of energy consumption 1416 MUs. So next let's move on to the RE details state-wise in southern region. So in this slide the state-wise penetration is given. So of this the maximum is in Tamil Nadu, accounting to 20 gigawatt, and then followed by Karnataka, 14 gigawatt. So this is the level of penetration at state level, state-wise in southern region. So these are the beginning slides. So I wanted to give like feel about the quantum. So now let us move to the second part of the presentation, that is on the protection issues due to the RE penetration. Yeah, these are, we also have one integrated renewable energy projects. So the integrated renewable energy projects are like the projects wherein which you will have solar, wind, pumped storage, everything together. And a few other, we also have some integrated renewable energy projects wherein which will have solar, wind and battery storage. So along with storages, we'll have the renewables also. So like that also we have systems in southern region, all are being in commissioning stage. Many like installed capacity is so much, but half the way, they are in half the way. Yeah. First protection issue that I want to highlight today is about the impact of the RE on the earthfall protection. So in transmission system, we have the earthfall protection, mainly to take care of the high resistive faults. Otherwise, the main protection is distance and differential protection. So earthfall protection is to take care of the high resistance fault in the system. So with the IBRs, what happens to this earthfall protection? We are going to discuss now. What is happening exactly here is IBRs cannot contribute more current, unlike our conventional generators. So here, due to the reduced short circuit current, it is not feeding the Whoever is not talking can please mute. So the conventional system will contribute high fault current, whereas the IBRs, they'll contribute very limited short circuit. Because of that, what is happening is during the fault conditions, the interconnecting transformers, IDTs of the IBRs, they are grounded. There is some looping of zero sequence current through this interconnecting transformer, and that contributes to the presence of zero sequence current. So when a fault happens, we expect the negative sequence current to be there from the generator so that we can detect that and clear the protection. But in this case, there is no negative sequence current. What we are seeing is the zero sequence current. Because of this zero sequence current, the earth fault protections, which are very sensitively set, they can maloperate. So when the threshold reaches, when the zero sequence current reaches the threshold of the DEF element, the directional earth fault component, this kind of maloperation can happen. So to show this, I have some case study. So let us take first case which there is a fault in the 400 kV system. That's a 400 kV grid connected system. There is a fault. And here we are having solar at 33 kV. It is getting connected. And this is 220 by 33 kV transformation. And then here we are having the grid station. So this is called the POI. This is a grid point, and this 220 kV, this is called POI. So now the point is, the fault is after the POI, that is, it is a grid fault. During this time, what happens from the grid end, from here, there will be a fault feeding to this particular thing. And from RE end also, some current will come from here. So the current what comes from the RE end, it is kind of a zero sequence current. So it will be like this. So the R, even though the fault is there in only one phase, in this case, there was a fault in B phase. The fault was in a 400 kV line connected to Devanahalli substation. So what we see here are the PMU plots. So in that particular line, due to the presence of auto recloser, that particular faulty voltage, and then it has reclosed. So it is coming back. The voltage is coming back. This fault was a transient fault. That's why at the time of reclose, we are not seeing any dip. So if you see the reflection of this Devanahalli line fault in a nearby station, let us say Tumkur we are seeing. So these are the stations in Karnataka. So if you see the reflection of this in Tumkur, it is something like that. Only a transient fault in signature we are seeing from the PMU, indicating a dip in the B phase voltage. So the B phase pole of this line, particular line, has opened and it has reclosed, and there is no persistent fault. Whenever the fault was there, during that time, we will be having the negative and zero sequence current in the grid. So these are all grid side things. So this end, what happened, I'm telling. Later, what happens at the RE end? This particular RE will have two protections, main one and main two. In everywhere we will be having main one and main two for redundancy. So of this, one of the main didn't respond, no indication, whereas the second main protection, it tripped. This relay gave trip on 50 N, 51 N, that is directional earth fault protection. So it had given the trip. So if you see the currents, they're all like in phase because it's a zero sequence component. It is the I naught, like IA, IB, IC is same as the IN. So that it is like a circulating zero sequence current. So conventionally fault is there, only the increase in the fault B phase current will be there. Because of RE, we are seeing this kind of signature. So this same amount of current would have reflected in the neutral. In this particular DR, we are not seeing the neutral IN, but if you see, it is the same current. That is the zero sequence current. So the directional earth fault protections, as I said, is a very sensitive protection. The pickup of these protection schemes are very low. Like typical protection at typical pickup at primary will be 200 ampere. So when that pickup is 200, if it is going to 600 and all, obviously it will get picked up. And however, 200 pickup will not operate immediately because it will have some IDMT characteristics. As per that, it will operate. But if we have enabled high set without any delay, then it is prone to maloperation. So in this case, it had maloperated. So if we see, this is the RE evacuating line at RE station. That is this DR. This DR I'm showing. At this end also same thing we will see, because it's basically a circulating current. At this end also same thing we will observe. So this is at RE end, this is at the grid end. So you can see the same current is observed. So it is all same in all the phases, zero sequence current. So in the grid connected station, there is only pickup, whereas the RE connected station gave trip. So later we came to know that they had enabled this high set component without any delay. So because of that, this particular maloperation had happened. So this is one impact. So now we are talking about the fault in the grid and the impact of the 220 kV RE connected evacuating line protection. Similar thing also happened when there was fault in the evacuating line itself. There was fault in this line, 220 kV evacuating line itself. So this line, I'm calling it as an RE evacuating line. So this portion is grid and then only RE is connected. So this is what I'm calling it as an evacuating line, 220 kV evacuating line. So in the next case, there was fault in this particular line, 220 kV evacuating line. During this time also same thing happened. From grid end, we had actual fault current contribution, whereas from REN, we saw the zero sequence current. So this particular DR also, I have, instead of showing in the DR format, so plotted in Python so that we can understand the difference. So I'll try to explain from here. So the blue one, solid line, is the current from REN, and the red dotted lines are the current from the grid end. So first let us see the grid contribution. During the normal condition, there was no RE generation, so it's like almost 0, 0 only. All of this is IE RMS, this is IY RMS and IB RMS of both grid and RE end currents shown. And here down we are seeing zero sequence IMS, RMS, and then positive sequence current, negative sequence current of both grid and RE end. That is this current, and this current, both we are seeing now. So when a fault happened, so we can see here IRMS, IR phase, Y phase, B phase, all are same in case of the current from the grid. And the zero sequence, and if we see the current from the RE end, like there is no fault contribution at all from the RE end. Only from the grid end we are seeing the fault contribution. And we can see the negative and zero sequence component also. The negative and zero sequence component are also present only from the grid end. The grid end is having this zero sequence current, positive sequence current, negative sequence current, all the currents. Whereas the RE end, it is having only the zero sequence current, which is getting reflected in R and Y and B of RE end, not on the grid end. So this is the thing that we are observing. So if we see here, the zero sequence current, it has gone as high as 1.8 kilo-amp. So 1.8 is a very high pickup for a earth fault protection to operate. So in this case, the high set earth fault protection operated because of this zero sequence current at the RE end. So that is regarding the impact of RE on the earth fault protection. So what are the factors that this zero sequence current depends is on the grounding of these interconnecting transformers. So we tried to simulate the same in PSCAT, and we were obtaining the same results. This kind of behavior not only comes when we have IBR, but also in the weaker system. When we are having radial loads connecting to the grid and where the system is very weak, that means it cannot contribute to the fault. During that time also, the presence of zero component current, sequence current we have seen, and there are many literatures on the tertiary contribution of transformers like that. So meaning that even though the system is radial, through the tertiary of the transformer, we are seeing this currents and impacting the protection. And few vendors are coming up with adaptive protection schemes. This itself they are taking as advantage. Instead of sensing the negative or zero negative sequence component, the relay logics are being changed by sensing the zero sequence components. So those kind of literatures are also available. So next, we will quickly see about the impact of RE on distance protection. So distance protection, I hope all of you are aware of distance protection. So here what happens to the phase and the ground loop because of the presence of REs. So this kind of impact on the distance reach related issues can be there, but particularly because of RE, such tripping we didn't observe at interstate level. At central grid level we didn't observe, but at state level we have observed. So that case I have included in today's presentation. So what happens here is the fault current contributions from the IBR and the grid, they exhibit large difference. What happens in a conventional system? So when a fault occurs, both the sources are contributing. And if we compare the angle between these both sources, they are relatively low, like less than 10 degree. Whereas when we have a IBR and the other end source, the angle between the sending and receiving end depends on the control of this IBR, and it can vary. There can be a larger variation in the angle. Why are we bothered about this angle is the distance relay calculation, the phase loop and earth loop. In their calculations, this angle is involved, and because of this, there is a correction factor involved. We are simplifying the phase loop and the earth loop, and assuming this angle variation is difference, very minimal. If that assumption is not valid, we will have one more component, and that component can be a plus or a minus, depending on the variation of this angle. So when it is plus, the relay will overreach. When it is minus, the relay will underreach. So that is how the RE is impacting the distance protection. One more thing, what we are observing is there is due to the lack of short circuit contribution, the voltage collapse condition happens, and the distance relay is peaking under those conditions. Because even though the current is not high, when the voltage is becoming very low, then also the characteristics are coming inside the impedance loop. So they are typical examples for the impact of RE on the distance protection. So this variation in the angle between the grid end and the IBR end, we call it as a non-homogeneity. So many work is being carried out in this regard. So one of the adaptive thing is that zero sequence based thing and all. So the case study, I would like to present one event that happened in AP. There were multiple outages of substations on 25th June. So here, this is a grid connecting substation. There are two grid connections here, one grid and two. And this portion is completely radial because here we have only RE station and there is a load. And during antecedent, this particular line, this substation to this station line was under open condition. So this whole thing was radial. And the fault was in the substations, the grid connected substation, bus fault was there. So when this bus fault happens, ideally the bus bar protection should operate and clear this bus section, and all other elements connected to the other bus should stay connected to the grid. But what happened, there was this bus bar didn't operate. So because of that, the fault was cleared by the remote end. So the remote end also, a bus fault for the remote end should be sensed in zone 2. But we are seeing this RE station and the two RE stations sense the fault in zone 1. That means zone 1 overreach happened. Because of that, these two major evacuating line was lost. So all the RE connected to that particular grid also got lost. So there was a complete outage. So this is a real-time case. So when we looked into the DR, This is the kind of signature. Actually, the fault was RY fault, but this is what we observe. It will not contribute to the this is actually pre-event. So if you see the pre-event, this is the voltage, this is the currents, these are the currents, and these are the voltages. So currents were like 122 amps in all the phases, and voltage 127, 220 kV system. But what happened during the fault? Even though it is an RY fault, we are seeing this sequence current. So zero sequence current, and also in this case, zone 1 trip we are seeing. Zone 1 is getting tripped. So usually when we talk in terms of current, the zone 1 to operate, sufficient fault current should be there. But in this case, fault current is not there. But you see, the voltages have collapsed like anything. It has gone almost to 8 kilowatt, 230 kV system going up to 8 kilowatt. Because of this, the zone 1 is getting maloperated. Also, if you see the angle variations during the normal condition, if we keep the Y phase as a reference, 120-degree phase angle variations is there between the phases. During the fault, the angle variations between the phases are like this. So ideally, it is a zero sequence component. It will not have major phase angle between each. So this is one such maloperation of distance protection due to RE thing, because of lack of the negative sequence component, lack of fault contribution from the system. So that is about the impact of distance. So in this case, actually, the remaining grid end also cleared the fault finally. But major issue was with the RE overreach. There were multiple failures of protection system in this actually. So next is impact of auto recloser, impact of RE on auto recloser. I hope all of you are aware of auto recloser. So in India, for the transmission system, even a distribution system also, few places we have this three-phase group operated auto reclose. So our transmission system, it's mandatory from 220 and above lines. Auto recloser is mandatory because most of the fault in the power systems are of transient type. 80-85% as we study in the textbook, and it exactly matches with the real time also. That's what we also observe. 85% will be based on single line to ground fault. That being the case, given a chance for the fault to get cleared, there are many chances that we can get back the line without losing the reliability. So that is why we go for auto reclose. So for during transient faults, the auto recloser will open and then it will reclose after 1 second. So as per IEEE standard, based on the deionization timing, arc extension time, 1 second is decided. So that dead time is 1 second. After 1 second dead time, the breaker will try to reclose. If fault is persistent, it will lock out. If fault is not persistent, then we are getting the line will be reclosed and the normal operation will be resumed. So that is the thing. So whereas in this RE evacuating lines, we are facing this issue. Most of the cases, auto recloser will not happen properly. And ideally, we expect it to happen properly. So one such case is presented here. There was just one RN transient fault in the system, but the evacuating line didn't attempt for auto reclose. It tripped. It had sent a direct trip to the grid end, and both the ends got tripped. So in this case, there was a differential protection. Most of the REs connected at central level are having differential protection. So this homogeneity kind of issue, what I discussed previously, can be avoided to some extent, or to greater extent we can tell, in differential protection. Differential also, if the angular variation is between the grid end and IBR end is very high, then differential also can maloperate like that. Literature is telling. So we have not observed so far any such tripping. So most of the RE connected at central level are having differential protection. Maloperation of differential protection is, very minimal only. Only the thing is, in case if communication failure is there, again, it will come to distance. So in this case, again, coming back to the auto recloser issue, why auto reclosers are not operating in RE connected evacuating line? So the problem comes when we have only one RE evacuating line. If we have two lines, anyway, through grid end, even the RE connected end, there will be fault contribution. So auto recloser operation also they can happen. So in single evacuating line, the issues are like what RE developers are telling is they will lose the reference voltage, like that they are telling. So if one phase is not available, my PLL will not have a reference voltage. PPC will not have a reference voltage. So operation cannot happen. It will trip, inverters will trip. That is what they say. But through simulation studies, what we are observing is when you consider a auto reclose condition, that is during the dead time, two other healthy phases are available. That means your net positive sequence voltage, if we see, it's like 67% is available. So when you compare this with the LVRT curve, it's well within the curve. So auto recloser should operate, but few RE OEMs are saying there are some issue. Few others are telling it is okay. So that is the thing. So when we studied with respect to few inverters in the simulation, it is performing correctly only, and we feel it should be in service. So wherever this auto recloser non-operation thing, so we are asking them to enable, and we are asking them to remove this sending of direct trip scheme. And next is the protection coordination related issue. So this can happen in conventional system also. Whenever there was a fault in one place, the upstream feeder should not trip. So here what happened, we have most of these 3366 kV from the RE plants, they are out of cables. So there was fault in this interconnecting cable. And for that, the 220 kV system, directional earthfall protection maloperated, meaning there was no coordination between this overcurrent, and usually 33 kV it is overcurrent only. And for 220 kV, only the earthfall is overcurrent. Otherwise, it's distance or differential. So that backup and this overcurrent protection coordination was not done. Because of that, we lost the grid line. So those kind of trippings we had observed, some 3-4 trippings are there. Then coordination was ensured. The pickup and time settings were changed. So this is shown to say that there was no delayed fault clearance. Only when there is a delayed fault clearance, if this is not operated, then transformer should clear the fault in backup overcurrent. If that also has not operated, then only this 220 kV line is supposed to operate. That also, it should not see this fault because it is not in its direction. So here the non-directional earth fault protection has operated. So it should be directional. So in this case, the direction, pickup and time setting can properly changing as setting will avoid the overcurrent protection maloperation. So these kind of coordination issues can be avoided. So next, I want to share a few things regarding the LVRT non-compliance issues. So now we saw mostly on the grid side faults and grid side protection systems. So I would like to next touch upon grid side fault and how the inverters have behaved. So that is where we talk about the LVRT and HVRT compliances and all. So in the previous session also, the speaker was explaining about those testing and all. So before any model gets connected to the grid, we collect the testing of the model and we check whether it is proper or not. Then only the connectivity and all is given. So here what happened was 30th August, there was some RY fault in 33 kV feeders of the RE station. So for that fault, 220 kV line was intact, but the RE, the IBRs got tripped. The WTGs connected at 33 kV got tripped. So it is the non-compliance of LVRT protection. because the voltage is within the LVRT limit, still it that few inverters have tripped. So if we see this side, we are having the RE station voltage, all the three phases voltages. So we can see initially there is a dip in R and Y phase. Subsequently, there is dip in R, Y, and B phase voltages. And if we see the P and Q of the plant, initially the plant was evacuating 227 megawatt. So after the event, it has reduced to 108 megawatt. There were 333 kV feeders had fault. Anyway, when they got tripped, some amount of megawatt will go. But beyond that, additionally, we have seen the WTGs getting tripped for the fault in the feeders. So only when there is fault in the WTG should trip. For fault in feeders, and when the voltage is within the LVRT limit, the WTGs are not expected to trip. So in this case, we have observed tripping of the WTGs. And during the fault, as per the regulation, they can active power can go down because the reactive power is only given preference. But once the fault is recovered, within 1 second, 90% of the pre-fault megawatt should be recovered. So these are the grid compliance regulations requirement, but it didn't happen. So in this case, there was loss of 138 megawatt. So one case of LVRT non-compliance. So we have checked the feeder-wise flow also. So this is from the SCADA. So like this, some LVRT related issues we have observed. And then one another case happened in a station near Pugalur. So here also there was a fault in a 400 kV Pugalur connected line, and it was RY fault. One more thing, most of the time when there are face-to-face fault only, we saw the IBR's behavior, IBR gets tripped based on the severity of face-to-face. Usually for face-to-face fault, face-to-ground fault in the grid end, we have not observed major tripping of IBR. During face-to-face faults, many trippings are there. So in this case, we are seeing delayed response in the megawatt. The green color line indicates a megawatt. So antecedent, the megawatt generated from the plant was 220 megawatt. So this is also wind plant, 220 megawatt. After the event, it is 196 megawatt. The event happened in the grid. It is not related to the RE. So for grid faults, the IBRs shouldn't have tripped. So that we have observed. We have the PSCAD model of the system, but when we study in the simulation, we are seeing proper response. Like it is coming back. You can see at PPC, the megawatt before and after both are same. So this is VPPC. So the same dip in the voltage was applied. So at grid end, this is the dip. Yeah. Next is also an LVRT related non-compliance. So in this case, there were multiple RE stations getting connected to one pooling station, and that pooling station is connected to the grid. So in this case, what happened? There was a fault in the pooling station. So this happened in Karnataka, and in that pooling station, only one bus section was faulty. So which was connected to RE station 1. So the tripping of that line is in order because it is the tripping of the bus bar operated. The line connected to that bus section got tripped. Whereas, and when we look into the voltages of the other RE stations during this fault, the RE station 2, it had reached up to 80 kV according to 0.63 pu, and RE station 4, the voltage went up to 0.61. So these, and the fault got cleared within 80 milliseconds. So again, these are also within the LVRT curve. But we had seen the one of the RE evacuating line got tripped on operation of SOTF protection. Switch on to fault protection. So I hope all of you might have heard about this SOTF function. So the requirement of this SOTF function is like, let us say some line has stripped and we are attempting to charge the line. At the time of charging the line itself, let us say there was fault. Whenever we charge the line, we charge first from one end, then the other end. Preferably if generating and substation are there, from substation end only we close it. Also, we see the voltage conditions at the remote end, whether it's long line or short line, whether line reactor to be taken in service or remote and bus reactor to be taken in service, like that. So when we charge a line and if there is a fault in the line, we don't have to wait for zone 1, zone 2, zone 3 and all to pick up. Immediately we want the line to trip. So that is called switch on to fault condition. So it will basically see the breaker close. This particular function will be active only for some time from the closing of the breaker, and the logic for this can be either distance or differential. Sorry, overcurrent. So if it is distance, it will be set up to zone 2, zone 1, zone 2. Usually if it is zone 3, then it is assumed that the fault is beyond, it is then some other line. But if the remote end is not picked up, remote is open, if the line is like ideal charge, then obviously the fault is there in the line. So for that kind of protection, for early clearance of the fault, we have this function called SOTF. So during this particular event, this line, which was already in close condition, got tripped due to the SOTF maloperation. So this particular issue later it was rectified because that SOTF enable function was manually set high. Due to that, when fault happened in a nearby thing, when the current had pickup has reached and the SOTF initiation was high, due to that this particular RE evacuating line had tripped. So later in that relay, high SOTF during the manual high SOTF function was changed. So it was made auto. So due to that, this RE evacuating line got tripped. Later for the other RE stations, that's RE station 3 and 4, which were connected to that pooling station, we didn't observe the tripping of the evacuating line, but LVRT non-compliance was observed. For example, this station 3, it was generating around 146. So after the event, it should have recovered within one second, but there was delay in the recovery. It had taken almost like 6 seconds. And in RE station 4, there was some tripping also. Few WTGs, like 1 or 2 got tripped. Maybe 3 megawatt if we see. Few WTGs got tripped. So that the corresponding PMU plots are shown here. So the RE station 3 and the 4. So some megawatt loss and the delay in the megawatt recovery was observed. So in this case, it was RB fault. So we are seeing dip in the RB, R phase and the B phase voltages. And here we are seeing the megawatt and megawatt. So during the fault, megawatt is going high, megawatt is coming down, and it is getting recovered. In this case, it didn't recover at all. Like there was tripping. Immediately the inverters will trip and they have to restart. That restart didn't happen here. So for that also, inverters are having many protection. Like a few protection of when it gets operated, the inverters will auto turn on. Few protections when operated, the inverters will require manual switch on. So that depends on the type of the impact of the grid fault. Like some sink will require the manual turning on of inverters. In that case, the grid compliance of 1 second recovery will not be met. So this is the station 4. So here it is coming back, but the time taken, the ramping was not met, requirement not met. So that is regarding the LVRT non-compliances based cases. So this is also one such delayed recovery of P and Q. So this also happened in Pugalur only. So here RY fault in the station. During that time, we can see this P and Q responses are not in order. So these kind of issues, whenever we observe, we conduct meeting with that concerned OEM and we get to know the issues, why it didn't operate, why the inverters got tripped, why it didn't restart. So based on their reply, and we suggest some corrections, and then after taking the corrective actions, we have seen these kind of trippings have come down. So in few cases, the WTGs usually the inverters will trip on the synchronization related issues, and the anti-islanding systems will get maloperated. The anti-islanding scheme, which is designed to trip, the islanding scheme, which is designed to trip in case of loss of evacuating line, will maloperate during the transient fault in the grid. So due to that, some phase displacement protections will operate, tripping the inverters, WTGs, everything. So then we have changed the angle and threshold for that. So sometimes due to transient variations, they will get tripped. So those kind of things and all we have observed and we have changed. Then during a few cases, the WTGs have tripped due to firmware issue also. So those places firmware upgradation was done, and in few places due to delayed response, it has tripped. The control loop delay was there because of the WTGs had tripped. Then the control loop algorithm was changed, mainly based on the DC or unbalanced protection that used to happen, and because of that the WTGs were getting tripped. For that DC unbalanced kind of thing, the control loop mechanism itself, few OEMs had changed it. I'm not mentioning the name of the OEM here. And what exactly happens there is, whenever AC side faults are happening, some DC side unbalances are also happening. So if this DC side unbalance is not within the threshold, then the DC side unbalance protection will operate. So the DC side control loops are map, like algorithm is managed in such a way that the variations are controlled during the grid fault. In that way, they had taken some corrective actions. So there are various cases and various types of actions taken, and both the issues we are seeing, network side issue as well as the inverter side issue. Both the sides, many issues were seen and many corrective actions were taken. And the over voltage related issues. So whenever there is no generation, so if we see this solar cooling station, 400 kV voltage, during the this is like, if solar generation, if you see, it will be like this. So the opposite of that is the voltage. So during night hours, and that means non-solar hours, the voltages will be very high. And the wind also, depending on the wind availability, the other time the voltages will go high. So usually over voltages are there. And because of this, at 400 kV line, we have 400 kV side, for the lines we are having graded over voltage protection. And for 220 kV lines, we don't have over voltage protection. We ask everybody to disable it. The 220 kV over voltage protection is taken care by the overflex protection of the transformers only. So sometimes that if that can also maloperate if the settings are not kept in order as per the design. And 400 kV side, the as I said, we have a graded over voltage protection, because when the voltage goes 110%, we don't want all the lines connected to that particular substation to get tripped. So whenever one line gets tripped, based on the reactive power relief, the voltage will come down so that the other lines can stay in service. So most of the time, these over voltage protections of the line, they are like very sensitive. they'll not have a higher drop off to pickup ratio. So because of that, some maloperations can happen. So other reasons for over voltage related maloperation is the CVT drift. Actually, over voltage may not be there, but that because of drift in the CVT, one of the phase may read slightly higher voltage, and that particular phase will trigger the over voltage of protection operation, and due to that we may lose the line. So those are some of the maloperations related due to over voltage issues. So in general, so quickly I have tried to cover. These are major protection challenges that we encounter in grid due to the REs. So we can discuss now if there are any doubts.
We have 2 questions in the chat box, ma'am.
Yes, sir. Welcome. Sir, as of now, this penalization and all is not there. OEM control regarding black box control, it is not they are not giving. So that is why we are not able to see what is the response of the like why it has responded to that like that. We are not seeing. Moreover, we don't have the high resolution data of the inverter itself. How the inverter behaved is most of the time lost. Only at grid level with the available data we are able to analyze. So that is also another issue. But the model that is given is not a detailed model most of the cases. So nowadays few detailed models we are receiving. But whatever events happened without proper high resolution data, we won't be knowing also how it has how it had operated. We won't be knowing also. Based on the logs and available SCADA and PMU data, we are saying that now it as in IEGC 2023, this high resolution data is mandated. So now whatever RE that is coming now, like they have to comply.
Thank you, ma'am. Participants, if you have any other questions, you can ask now. Ma'am, one more doubt, ma'am. When you are presenting, you are saying that there are some adaptive schemes are available based on the zero sequence current. Whether Grid India will apply a new innovative algorithms that are being developed, or it will only focus on the conventional schemes that is already available?
Sir, like Grid India is not into the relay algorithm development. Like based on our experience from the operational data we are telling. So those works are done by the OEMs, sir. Like Hitachi is proposing that zero sequence, and many other OEM. Siemens is telling some other things. Some virtual V by F, virtual X component in the relay. Like that, the OEMs are suggesting that, and that is not covered in the grid code yet.
Thank you, ma'am. One more question you have on the chat box, ma'am.
Yes, sir.
In grid operation, whether we will follow IEC or IEEE standards?
Usually we have like in grid operation we have Indian standards only. IEGC is there, CEA technical standards are there, CERC regulations are there. But whenever the changes are coming, we take input from IEC, IEEE, SIGRE, everywhere. And we can take input, but whatever comes into our regulation only is final. I cannot mandate somebody because IEEE is telling. Because of Indian regulation only, I can mandate. Like I can back up use from references from there.
Thank you, ma'am. Participants, if you have any other doubts, kindly ask now.
Good evening, madam. Thank you for the informative presentation.
Thank you, sir.
Suppose if we want to collaborate with the Grid India for in this kind of study, what is the channel? How do we approach? Because we have software.
So we have MOUs with. Yeah.
Software in
Yes,
our
sir. We
institute.
have MOUs. You can like with MOUs also we can sign and we can give you some projects. Like we have MOUs with IASC. They are developing one grid forming inverters. So like that with MOUs we can with respect to one MOU some project can be finalized. Like that some collaborative work can be done. Yes, sir. Those kind of things are going on. Like at IIT Bombay also WRLDC is involved. Some PMU analytic based things are there. With IASC this grid forming inverters, grid following also is that. Now grid forming. Earlier grid following was that. Phase 2 we are doing. So like that with institutions it is there, and a few institutions there are like mutual knowledge sharing kind of things are also there. So you can approach our HR like how we can go ahead with few institutions that students get the internships. So for 1 week, 1 month, 2 months, like that, some minor projects that is also there.
Thank you, ma'am.
Ma'am, how it is difficult for Grid India to operate Indian grid with a great share of renewables, ma'am? What challenges are in operations, ma'am?
Yes, sir. Other things what we are facing in day-to-day operations are mainly the flexibility. When the REs are getting peaked, we have to back down the thermal. So due to this, many variations in the scheduling related issues are more. We are seeing the RE states underdrawing suddenly, overdrawing suddenly. So here impact of forecasting comes into picture. To some extent forecasting is there, but we have to work more on that, and flexibility also. And so to tell, I will say flexibility, the forecasting related issues, and then the system strength. Where we have lot of RE in a complex where there is low short circuit, it is more prone to more disturbances and higher losses of RE and larger grid frequency variations. So short circuit related issue also we are facing there. So whenever that RE is getting connected, so with proper study only we can give that connectivity and all. If low short circuit is there, what happens is during LVRT conditions and all, after LVRT conditions, during at the time of recovery, we are seeing higher variations in the voltage, high voltage. Because of that, the transmission lines are getting tripped on over voltage protection operation. So due to low short circuit ratio of a bus, larger support from RE is expected in terms of reactive power. So the RE is pumping more reactive power during the fault. When the fault is actually getting cleared also, the reduction in the reactive power is not immediate. So post-recovery fault, we are seeing high voltage. So that high voltage, because of that, the lines are getting tripped. Then final entire complex getting tripped. Those kind of issues we are seeing. So that is like a third one, I will say. Then we are facing oscillation related issues also. This is also because of weak interconnection. And because of RE, we are seeing oscillations in voltages and currents, and due to that, REs are getting tripped. So that is another issue. And most few cases in SR, we have observed like that one oscillation in one plant, and later the voltage control of the plant was changed. With that revised voltage control, nowadays that oscillations we are not facing. But in northern region, it is like we are facing regularly, and major outages are happening because of northern region RE related trippings. So these are some of the major things that issues, and also market wise also, without proper forecasting, that excess power you cannot push in the real time markets. So nowadays, earlier it was the conventional real time market. Now it is like green real time market is also coming. Market coupling, everything is like under progress. So we are still on like developing, working on those things.
Thank you, ma'am. Ma'am, while explaining the homogeneity, you have shown one curve, ma'am. Whether it is an actual curve or it is a simulated one, ma'am. You have shown a curve showing the angle difference of the two ends.
Yes, that was from that IEEE one work group set.
Oh,
IEEE work group, yeah. Actually, for the I showed you one case of distance maloperation in AP where multiple substations were tripped. So in that we had the DR of the REN, but we don't have the DR of the remote end because the remote end will not pick up. It has to pick up in reverse zone, but that DR we didn't have. Actually, it was a bus fault. If we have both the and DR, then we can study that non-homogeneity set. But the problem here is that and DR we didn't have. But still, we could have checked the next level station so that the sending and receiving in both are there. Now the problem comes, the DR of that and the DR of RE station will be of different sampling, different trigger time. That being the case, getting the angle between both the waves becomes difficult. So such kind we tried even for conventional from the DR when we try to get due to the difference in DR trigger time between the sending and receiving end and the DR sampling frequency. So few DR it will be 1200 hertz, few thousand hertz. Because of that, we are not able to properly get that angle difference for a actual event set.
Thank you, ma'am. Ma'am, in the load display center, whether you can able to directly get that DR records and all directly, ma'am, or you have to go
Yes,
to that
sir,
location to
as
get that.
per No. As per IEGC, it is mandatory. Whenever an event happens in the grid, within 24 hours, they have to furnish the DR to us. So we have a portal, a separate portal. Whenever tripping comes, it will be automatically added in that portal because within 24 hours, it has to come. So if a particular 400 kV or a 220 kV interstate line is getting tripped, the concerned user will intimate the control room. Control room will add it in that portal. The moment it comes in the portal, the users will upload the DRs in the CFG DAT file. So that we analyze and we check whether the tripping is in order or not. So not only RE, like conventional also, all we try, all we check.
Thank you,
And
ma'am.
substation, if you ask, there are like most of the substation, there is like RAS, automatic DR will come. Like even in one station, there is an automatic fault analysis also of us pilot project in Tamil Nadu, Palavadi. Most of the power grid stations, like this RAS is there. Without going to the relay, they can get the DR in the remote server. Old stations and all that some RT person will go and collect the DR and then only they can upload.
Thank you, ma'am.
Yes.
Participants, kindly, if you have any questions, ask now. Otherwise, we will wind up the session. Dear participants, if no questions, we shall wind up the sessions. If you have any question, you can raise or you can unmute yourself and you can ask the questions. In that case, we'll wind up the session. Thank you so much, ma'am. It was an excellent and wonderful session. And that gives a real scenario of what is happening in the Indian grid, ma'am. Thank you so much, ma'am. Now I invite Anuleka Pandey to give the vote of thanks.
Thank you, sir. Good evening, everyone. As we come to the end of this insightful session, it is my privilege to extend a heartfelt vote of thanks. On behalf of everyone present, I express our sincere gratitude to Ms. Aarti Sahaya Jones, B, Chief Manager, Southern Regional Load Dispatch Center, Grid India, for sharing her expertise on overview of RE and its impact on protection issues in the southern region of regional grid of India. Your deep insights into renewable energy integration and grid protection challenges have provided us with valuable knowledge and a fresh perspective on power system management. We truly appreciate the time and effort you have dedicated on this session. Thank you once again, ma'am, for this enlightening us with your expertise. A big thank you to all the participants for your engagement, and we look forward to more such enriching sessions. Thank you.
Thank you, madam. Thank you.
Thank you so much, ma'am. We have learned a lot of new things from you, ma'am. Thank you so much for that, ma'am.
Thank you, sir. Thank you.